The next set of reactions that we're going to cover in chapter 22, there's 3 reactions in this section, 22.5, and these reactions all involve alkylation, or putting an alkyl group or a carbon chain on the alpha position of a carbonyl. So these are important reactions because they create carbon-carbon bonds, so they allow us to lengthen a carbon chain. And we don't have a ton of reactions, like I said 100 times. We don't have a ton of reactions that create carbon-carbon bonds. So these are all very important reactions in terms of synthesis. So like I said, there are 3 different alkylation of alpha position reactions that we're going to cover. The first one is alkylation via an enolate. And in this reaction, so I'm going to use, for our example, I'm going to use an asymmetrical ketone. This reaction is going to work fine regardless of what kind of R groups might be attached to this carbonyl compound. It's a 2-step reaction. So the first step is a base, and there's a pretty limited number of bases that you can use for this reaction, so I'll give you a list of what will actually work. And then the second step is to bring in an alkyl halide. And what you end up getting, so the base is going to deprotonate one of the alpha carbons, like maybe it's going to be that one or another option that wasn't very. So maybe the deprotonation would take place here, or this is not an and, or the deprotonation could take place at this alpha carbon, one or the other. And so you're going to make an enolate. And whichever alpha carbon you deprotonate, that is where the R group will attach, the R from the alkyl halide. It's going to end up going on whichever alpha carbon gets deprotonated. So our options for our base depend on where we want the alkylation to take place. If we want the alkylation to take place on the least substituted carbon, which is the first structure that I drew, you want to use our friend LDA, lithium diisopropylamide. And maybe sometimes you'll see this is a very cold reaction. So sometimes you'll see the condition -78 degrees. That's very specific. Sapling does not include that temperature condition on the reactions. So sometimes you'll see it, sometimes you won't see it, but the LDA part is a dead giveaway that's what's going on there. If you want to put the alkyl group on the most substituted carbon, then the base that you'll use for that is sodium hydride, NaH. And that will allow deprotonation of the most substituted alpha carbon. No temperature rules for this particular reaction, so it's any temperature. So let's talk a little bit about the difference between these 2 reactions. When we're using the LDA and maybe having it very cold, we say that this reaction is under kinetic control, which is a word that we've used, or a term that we've used before when we were talking about doing addition reactions to dienes, and we were controlling the reaction with the temperature. And if we had the reaction under kinetic control, that meant that we wanted the reaction to happen as quickly as possible. So it produces not necessarily the most stable intermediates or the most stable products. When we have this reaction under kinetic control and we're using a relatively bulky LDA base, it's not like tert-butoxide bulky, but it's relatively bulky. Bulky LDA base will deprotonate the least substituted carbon, alpha carbon, not any carbon, alpha carbon. And there's no rearrangement because of the temperature. So our alkyl group gets put on the least substituted carbon. When we're using the other base, sodium hydride, in this reaction, the actual base is just the hydride ion H-, which is tiny. And so this reaction, we say, is under thermocontrol or thermodynamic control. And that means that we are allowing the reaction to produce the most stable intermediates and ultimately the most stable product. The small hydride base deprotonates the most substituted alpha carbon. And in this reaction, because we're deprotonating the most substituted carbon, there's no motivation for a rearrangement, so also no rearrangement takes place. So we're going to look at the mechanism for this reaction in a second, but before we get into the mechanism, one more condition on the alkyl halide. We're going to see that this reaction is an SN2 reaction, so that means that the alkyl halide that we use can't be tertiary. So let's take a look at how the reaction works, the mechanism. And I'm going to use the same ketone. And we're going to, let's start by doing the hydride as the base. So the first thing, we got to think about where are all of the alpha hydrogens in this molecule. This one has 5. And then once we've identified all the alpha hydrogens, we have to think about our base and what is our base going to do. And since we have the small base, that means the small base is able to fit in to tight spots and crowded spots, and it'll go ahead and deprotonate at the most substituted alpha carbon because that's going to give us the most stable enolate. So that gives us this intermediate right here. And then once it gets deprotonated, we will bring in, I'm going to use like bromoethane, we'll bring in some sort of alkyl halide, and we'll just do a simple SN2 reaction on that alkyl halide. No rearrangements are happening, and we have successfully alkylated our ketone. For the LDA reaction, we're going to start the same way by identifying all of our alpha hydrogen, and we're going to ask ourselves, where can this base go? Where can it attack? Well, LDA is relatively bulky. Let me just draw its structure out. It's a nitrogen with 2 isopropyl groups on it and 2 lone pairs and a negative charge, so that's the LDA. And so because this is relatively bulky, it won't fit into the inside of that carbon chain. It's going to have to deprotonate out there on the end, on the least substituted carbon. So it gives us this enolate right here. And because we are keeping it cold, even though sapling doesn't always include the temperature, because we're keeping it nice and cold, it doesn't have the energy, the thermodynamic energy to rearrange itself to form a more stable intermediate. So it's just going to stay like that. And then it'll do an SN2 reaction on our alkyl halide. And that will give us this ketone.